Today we're gonna go over the story of two twin brothers trying to build high-performance buildings. This is Enrico. Enrico has an accent, is a total square, and is contracted to build a high-performance house. And his twin brother, Enrique, also has an accent, Googles a lot, and wants to build houses better than Enrico, as brothers do. Now, today's presentation is a follow-up from a previous presentation I gave, and I am including the link in the description of this video. And I would recommend you watching the presentation because other than the story of Enrico and Enrique, it also expands on other aspects of high performance and passive house projects that are very important. So please go find the link in the description of this video and watch that as well. But today, Enrico and Enrique go to Texas. So Enrico goes to Austin, Texas, and also Enrico goes to Austin, but Enrique wants to build a house more better than Enrico. So let's go to Texas. I've used my house project for this presentation as well. The original project is in Colorado. It's a remodel plus an addition. And just for the convenience of having the energy model already set up, I moved it to Austin and tweaked it to represent what we would do in a high performance or passive house project in a hot, humid climate such as climate zone 2A in Austin, Texas. This is a little bit of what the design looks like. It's on a ridge, but whatever, I moved it to Austin and tweaked it so it is relevant for hot and humid climates. So starting off from the floor, Enrico in a hot climate like Austin would not do no insulation under slab, whereas Enrique wants to do better. Plus Enrique found online some prescriptive approaches to passive house, and so he does 3 inches of XPS under slab. Then getting to the exterior walls, they both want to do R30. So Enrico does basically from the interior to the exterior the drywall, then specs cellulose in the 2x6 stud cavity, tapes the seams of the plywood sheeting as the air barrier, and then does 2 inches of polyiso as exterior continuous insulation, and then does a rain screen system. Whereas Enrique uses the drywall as the air barrier, uses the same dense spec cellulose in the 2x6 structural cavity of the walls as Enrico did, and then uses the R12 zip R sheeting rain screen. Then for the roof, Enrico does 15 inch of dense spec fiberglass for insulation and uses his smart vapor retardant membrane as the air barrier. Whereas Enrique does the drywall again as the air barrier and does 8.5 inches of closed spray foam as the insulation. For windows and doors, because it's climate zone 2, Enrico chooses double pane glass. We're gonna see later what Beefy means. C-grade frame, and Enrico goes with Argon fill for the glass unit and does an Innie install, meaning that if this is the wall section for the project, you see that the windows is installed in the middle of the wall thickness. Whereas Enrique wants to do better than Enrico, so goes for a triple pane. It goes for a triple pane installed on a regular conventional frame, which is also a C-grade frame, but because of the C-frame, because of the mainstream frame can only accommodate so much of a thickness, that triple pane ends up being skinny. We're going to see what that means in terms of performance. And Enrique found online that the Argon fill goes away after just a few years, so why bother? So instead of an Argon fill glass unit, Enrique chooses air fill. We're going to see again what that means in terms of performance. And then for the install position, Enrique installs the windows all the way to the exterior because that is what he's been doing for a long time, so that is what he does. Then for the ventilation system, Enrico uses a centralized whole building system with about 87% heat recovery. It's an HRV, so there's also some moisture recovery, and it is ducted. Whereas Enrique uses a ductless HRV with 89% heat recovery, so a little bit more energy recovery or heat recovery for Enrique. And they build the building, they get to the blower door test, they both hit 0.6 air changes an hour at 50 Pascal. Yay, happiness, happiness, joy, joy. So getting to the closure of the project, the expectation is that Enrico is going to have a certain amount of energy consumption for heating and cooling, and Enrique wants to do better. He invested in the triple pane window, the under slab insulation. So he didn't really do an energy model, but he was guessing or estimating 30 to 40% less heating and cooling compared to Enrico. So this is the finish line. We got the indoor air quality, the thermal comfort, the moisture under control, energy efficiency, feels good, happiness, joy, joy, puppies, kittens, and of course the puppies and kittens are Texan. Feels good, and we meet the expectation of the client until we don't, because day one Enrique's building already consumes much more energy than anticipated, and Enrique has gone out of their way to get a premium, pay for the triple pane windows, did the under slab insulation, all of that, and the building actually falls short on performing that well. It actually performs, it consumes just it's just 2% more efficient than Enrico, but Enrique paid for the premium for the triple pane and under slab and all that. So this is where, in the previous presentation that I again invite you to look at the link, we talk about performance gap. You find the link in the description of this video. That is something very common for buildings that don't follow a very structured process such as passive house. And Enrique, in addition to that, also has condensation. So something that really didn't want to happen. Condensation is bad. There's going to be a lot of problems having condensation. So we will want to see what happened in Enrique's project. So what went wrong? We just saw this. We have a performance gap. That is, we had an expectation about how the building was going to perform, and now the building is performing worse in that we have higher heating and cooling than expected, and we also have condensation. So we need to see what happened and how we can prevent this in the next projects. The C word in construction is condensation. For the sill details, this is just one of the many examples, but this is relevant. For the sill detail, Enrico decided to use vinyl flashing under the windows, whereas Enrique went with a metal sill pan under the window that is highlighted in red in the slide. So this is what Enrique did. And the issue with that is that any metal that bridges between the interior to the exterior is a thermal bridge. And there's a way to quantify the thermal bridges, which is the temperature factor method, which is part of the passive house standard, and is the part of the passive house standard that allows to prevent mold condensation by design. That is something that an energy modeler will need to do. But the long story short is that looking at the heat transfer in the detail, this stainless steel sill pan becomes a highway for heat to escape, and that causes, in the climate of Austin, Texas, where the coldest 12 hours of the year are about 24 degrees, that allows the interior temperature to drop down to 42 degrees, which allows for condensation. So this is a problem that is often not addressed in buildings because most buildings are very leaky. The better you start building and the more airtight your building becomes, the more this becomes an issue. And this is an issue that is often misunderstood with rain leaks, but it is not. This is condensation from the interior of the building that finds a cold spot because of the thermal bridge. In this case, the thermal bridge is the steel sill pan, and gets to condensation. So to have condensation, you always need two things: cold temperature and moisture. Inside the building, if you don't have leaks, then the biggest source of moisture is people. A family of 4 produces about 2.5 gallons of water every single day, which then stay in the house unless you vent it properly. And the other side of this is the closer we get to zero energy consumption in buildings, the more all of these details matter. So a stainless steel sill pan or copper sill pan or aluminum sill pan, any metal sill pan may not be a problem in a code minimum building with 3 ACH50 or an even leakier building because you have enough air exchange to the exterior. Air tightness is great for durability of the building, for indoor quality and energy efficiency, but it does bring additional issues to the table. This is what the heat flow looks again at the in the energy model. And if you look at the bottom right picture, under the window where the window meets the drywall sill and the exterior sheeting, that purple is all the heat that goes from the interior through the very, very thin steel pan to the exterior. In this case, in this picture, the steel pan is so thin you cannot see it, but if you were to zoom in, you would see a highway with high traffic of heat from the interior escaping to the exterior. That is something that came about in Europe about 15 years ago, where codes started allowing partial energy retrofits without really addressing the full picture of moisture management. This picture was shot by a colleague in Italy, where the building was built in the 70s, didn't have insulation, didn't have ventilation, had very leaky windows, air leaky windows, and so it was drafty, it was energy inefficient. So when the government promoted some tax breaks and incentives for buildings to become more energy efficient, the homeowners here said, oh cool, we can get new windows, get tax breaks, let's do that. And they did it. They installed brand new windows that are more tight, more airtight than the old leaky windows that were 40 years old. And in doing that, they made the buildings more airtight without addressing ventilation and without addressing thermal bridges. Again, to have mold and to have condensation, you need to have two things. One is moisture that comes from people and that stays in a house, inside the building. And on the other side, you need the lower temperatures. Now, in this case, in the house with the old windows, they had no mechanical ventilation, they had no active ventilation, but the windows were leaky, which provided unintentional ventilation. They had no control, but that removed some moisture. Now they replaced the windows, that moisture removal is no longer there, meaning that there's more moisture inside the building, and they didn't do anything to fix the thermal bridges. And in fact, what you see here, you see in the ceiling, you can very well read the rafters of the roof where they are over the white plastic, because you can read them in mold, as well as at the connection between the wall and the ceiling. You see a very big streak of black mold, because that is where there's a lot of heat loss and there's no mitigation for the thermal bridge. So this is something that physics does, because physics doesn't care if this is a retrofit or a new construction. If you have a combination of low temperatures and moisture, you're going to have more than condensation, which is problematic. And in fact, what we see here is the exact situation that Enrique had at the windowsill because of the steel pan. So we want to prevent that. Then Enrique also invested and paid for the premium to have triple pane, as opposed to Enrico sticking with double pane. Now, the expression double pane or triple pane is kind of misleading because the pane itself of the glass don't actually provide much insulation. It is what with it. The insulation in the glass unit comes from what's within the glass panes, typically a film of gas, air, or argon or krypton, as well as some low E coating, low emissivity coating on the interior surfaces of the glass. So in this, we Innie came up with the definition of or description of beefy versus skinny, because the overall width of the glass unit does contribute quite a bit to the overall performance of the window, and that is something that in general language is often misunderstood or not expressed, in that if you look at the beefy double pane that Enrico at the top picked, it's almost an inch wide from the exterior face of the glass, to the interior face of the interior glass pane. So 0.9 is kind of normal for double pane, or it's kind of a little bit beefy, whereas for the skinny triple pane, in this case, just the type of frame that Enrique had does not allow that triple pane to actually be very beefy. But that is very common. Many mainstream manufacturers of windows and doors have their frames all geared up for double pane, and it would be too expensive for them to have a wider pocket in the frame to accommodate for a beefier glass unit. So they sell you, oh, it's triple pane, but actually the overall thickness is still the same as the double pane. So you're paying for a premium, but you're not receiving the performance. So just to give you an idea, beefy triple pane glass is about 1.8 to 2 inches thick. So think about this. If you are comparing two options for insulation board, say your mineral wool insulation board, what provides you a better R value? A one board for 1 inch thickness or two half an inch thickness? It's the same. It's a trick question. But that is what we are sold for the skinny triple pane. They sell us the triple, oh, it's a triple pane window, so it's good, but it's actually very much underperforming. So looking at this a little bit more, the two columns here show the R value of the double pane, the beefy double pane on the left hand side, compared to the skinny triple pane. And you see that the beefy double actually has a higher R value than the skinny triple. So for the skinny triple, you're paying the premium, you're actually getting less performance than the double. So something that to be considered, because this is an area where if you're open to invest in more money in a project, everybody wants to help you spending more money, but you may not get the performance that you're looking for. And this is a very clear example of that. We see this all the time in our projects. You have a perception of getting a better product, but you actually are sold a product that underperforms. And in climates such as Texas and warmer climates in general, the sticker value for performance that you see issued by the NFRC, National Fenestration Rating Council, are really not relevant. The graph on the right hand side here shows in green shows the exterior temperatures over a typical year in Austin, Texas, from winter to summer to winter again. So you can see it ranges between 20 and 105 degrees roughly. You know, there's going to be hotter days, there's going to be colder days, but it's fair to say it doesn't drop colder below 20 degrees that often. Now, if you see the yellow line called out as NFRC, National Fenestration Rating Council, the NFRC rates all glass at 0 degrees exterior. So the sticker value that you see that tells you the U factor and whatnot, it's actually not relevant for Austin, because the condition that the NFRC rates the glass at never come by in Austin. So in other words, the skinny triple may look better on paper than the beefy double, but really it performs a lot worse because the rating conditions are not really relevant in a hot climate like Austin. Then looking at the exterior walls, Enrico had chosen 2 inches of continuous exterior insulation as opposed to Enrique that has 2 inches of the zip R, so the R12 zip R. And again, the closer you get to zero energy consumption, the more everything matters. So this funny blue picture that I just pulled up is a 3D view of the heat flow through the wall that Enrique has, which has the interior 2x6 studs with the dense spec cellulose, and then to the exterior it has the R12 zip R. And you see all those little pimple looking red dots, those are the fasteners. In other words, the closer you get to high performance, the more every single detail matters, and you do need to factor in the fact that the more metal fasteners you have through your insulation, the more your R value is degraded. And the difference between continuous insulation and the zip R is that zip R is sheeting, so it receives a lot more fasteners than the exterior insulation, about 4 or 5 times more nails and fasteners than regular insulation. And this erodes the R value some like 5 to 10%. And it's in the climate of Austin, you're perfectly fine doing a project with zip R. You just need to factor in that loss of R value in your expectation, because the closer we get to zero, the more all of this matters. So there's nothing wrong with doing a project with zip R in a hot climate like Texas, but you do need to account for that loss of R value if you're really trying to get your building to a high performance level. Then at the roof, Enrico had dense spec fiberglass and Enrique had spray foam, and the column graph at the center shows that closed cell spray foam performs very well in a lab, in that it achieves about 7 R per inch, but in the field it's very difficult to achieve that because of the ever-changing conditions of moisture and temperature, as well as the speed of application. So user error here is key, including the speed and how many passes we do the insulation, as well as choosing the right mix and choosing not to do a job when it is too cold or too hot or too humid. In fact, in Europe, the rating for spray foam is not 7 R per inch, it is about half of that, about 3.6 R per inch. You see the German standard at the top that calls out for that value. So all of this contributes to the underperformance or the performance gap in Enrique's project. So looking at the windows, this is the section view of Enrico and Enrique's wall and the window install detail. And if you look at that through the eyes of heat, you see how the position or the relative position of the window relative to the wall insulation is important. Starting from the far left, you see the rainbow picture, where the left hand side is blue, it's cold, it's the exterior, the right hand side is warm, it's red, and then you have a gradient of yellow and green with black lines on it, and those black lines are called isotherms, and the isotherms are lines with the same temperature. And isotherms, you want them to go nice and easy and straight throughout your details and assemblies. In fact, in Enrico's picture at the top left, you see that above the window there's the header, and you see that the isotherms fan out a little bit. This is a little bit, it's showing there's a little bit of thermal bridging there, but because it's wood, it's not that big of a deal. What is important on the picture on the left, looking at Enrico's detail, is that the glass itself is in line with the center of the wall insulation, meaning that very few isotherms have to go out of their way from the wall to meet the isotherms in the glass and then back out up at the wall again. So this is the reason why, if you're trying to optimize from a thermal standpoint the position of your window, the installed details of your window, having the window centered on the center of the wall insulation is the best way to do it. Now on the right hand side you see Enrique decided to go all the way to the exterior doing an Outie install, and you see how the isotherms had to, from the wall, if you start from the bottom, had to go up and then all the way to the left to meet the glass, and then when they go up they have to go all the way to the right again to meet the insulation wall. So this is why this is one use of geometry that Enrico does well, because the Enrico centers the window in the center line of the wall insulation, whereas Enrique sets his window off from the center line, and this offset is actually bad because it causes more losses. It causes more it's easier for the heat to go in and out of the building. So even in a hot climate like Austin, it's easier for the heat to get in, as well as it is easier for the heat to get out in wintertime. And another detail was that Enrique chose the ductless lunos and as an HRV, and they come with a very high label heat recovery. They have testing done for DIN 308, and this is unfortunately a very misleading and inaccurate testing standard. It is inaccurate because and misleading because in HRVs and ERVs, the only moving parts are the fans. And if the job of a fan is to move air around so that you have ventilation. Now, a job of an HRV or ERV is to recover heat, and an ERV also recovers moisture. Let's forget about moisture for a second. In the heat recovery, you measure the delta temperature between the air coming in and the air going out. And the higher the temperature delta, the higher the heat recovery. Now, back to the fan. The fan converts electricity to air movement, and a fan that is efficient uses it converts most of the electricity to air movement. A fan that is inefficient converts the electricity some to air movement and some to heat, because if the fan is very inefficient, it causes a lot of heat and it pushes out air not so much. So if you're trying to determine what is the heat recovery of an HRV, if your fan is inefficient, then you're reading oh, it's a high temperature delta, but it's actually the fan that is inefficient that is consuming more electricity, causing heat. So the HRV itself is not efficient. It's just a fan that is inefficient. And unfortunately, this testing standard does not account for the efficiency of the fan. So in the reality, while the sticker label is about 89 or 90% heat recovery, the actual heat recovery is lower. Casa Clima here tested at about 65 to 68. According to other standards, it's even lower, down to 20 to 40%. So if you're buying something that is rated at 90%, it actually performs at 20 to maximum 60%. You have not done a good deal. So lunos are great in retrofit of existing buildings to remove moisture to prevent mold. That is what these units were designed for in the first place. Don't expect much heat recovery from them because that is not what they were designed for in the first place. And for our exercise here today, we consider 68% heat recovery for Enrique. Then, so this is what we talked about for the day one performance gap. The right hand side is a repeat from the previous slide, and you see again, I would recommend you watching the video, the previous videos preceding this, because we talk more about performance gap. But in the graph on the left, the blue and orange graph, we have a breakdown of where the additional heating and cooling came from. You see in light blue is the expected cooling consumption for Enrico and Enrique, and in light orange we have the expected heating demand for Enrique and Enrico, because this is Austin, Texas, so much more cooling dominated climate than other climate zones. Now in darker orange slash brown and darker blue, you see the additional heating and additional cooling that Enrique's project is encountering because of all of these issues with the performance gap we just covered. So you see that Enrique paid a premium, but is actually not receiving the performance that he paid for. Then let's look at how this project evolves after 13 years. So in our previous videos, we talked about how an average American family stays in a house 13 years before they move out again. So we have the performance at day one, but let's see how these components age over time and how the performance evolves over time as people move in and stay there. So looking at the windows, we talked about Enrico choosing a double pane with gas fill, argon gas, and Enrique choosing an air fill triple pane glass, because Enrique found online that it doesn't matter to have the argon fill at the beginning. The gas goes away in just a few years, so why bother? Now day one, the double pane glass on the left that Enrico chose outperforms the triple pane with 4.5 R value compared to 4.1. This is the day one performance. And after 13 years, there is a performance loss for the glass for the argon filled double pane. But even after 13 years, so in general, a glass unit that is filled with argon or krypton can only be filled up to 90% gas fill. The other 10% is air. If you see a data sheet from a window manufacturer claiming that that window or that glass is filled with 100% argon fill or krypton, that's a lie. There is no technology today that allows to do that. Now, starting off from 90% argon fill, you can expect 1% gas loss per year. So after 13 years, you go down from 90% to 77%. And a double pane glass with 77% argon fill still outperforms a skinny triple pane with just air fill, 4.2 versus 4.1 glass R value. So this is definitely in favor of having a good argon filled glass, because the performance stays over time. Then at the floor, Enrique chose to do XPS insulation. At day one, that performs pretty well. Over the years, XPS loses the filling agent, so we can expect some loss in R values, about 20-25% over 13 years. So this was accounted for in looking at how Enrique's project ages. Then the air barrier, Enrico on the left had the polyethylene membrane under the slab in the air barrier connected to the sheeting of the walls, and then at the ceiling or roof, Enrico has a smart vapor retarder taped at all seams to be the air barrier. Whereas Enrique, on the right hand side, has the same polyethylene membrane on the slab, and then use the drywall at the wall and the roof for the interior air barrier. Now, looking at how this ages over time, there is research done on how buildings maintain their level of airtightness over the years. You see the sources here. It's the International Passive Institute as well as Proskiv and other sources. And we saw, we didn't look at just one project, we looked at about 24 projects, and they found that projects using drywall as the air barrier, the air leakage increases about 4 times more over just 10 years compared to using membranes, tapes, caulking, and specific products. So if you're trying to do a code minimum building and you're trying to just get down to 3 ACH or 5 ACH 50 as for Austin, then it doesn't matter. You know, that 0.2 increase in ACH 50 it's a 0.2 absolute, is not a percentage. It results in just about 6 to 10% increase compared to the initial test that you did once the building is complete. Now, if you're trying to do a high performance project such as a passive house, and your initial goal is 0.6 air changes per hour or less at day one, then don't use drywall. Don't use something that will become leakier and leakier over time. Because for a passive house starting off at 0.6, doing a 0.2 increase because of drywall, it means that your air leakage goes up 30%, which is very, very bad. Whereas studies show that even after 25 or 30 years, if you're using specific airtight tapes or caulking, you can expect minimal increase in air leakage over time. So airtightness can be very durable as long as you choose products that are durably airtight. So this is on the right hand side we see the performance gap, and in black we call out the increase in heating and cooling after 13 years. For Enrico, this is really limited to the little bit of gas loss in the window glass, whereas for Enrique you have a combination of increase in air leakage and loss in insulation value for the XPS. And on the left hand side you see the breakdown between Enrico and Enrique, and you see that over time how this changes with heating and cooling respectively. So thank you for this. I hope you enjoyed the Texan edition of the story of Enrique and Enrico. I may do this in the future. I don't know if it's a good thing, but leave your comments and questions in the chat. Thank you.